Hello. Um, Hello, welcome. Today I'll be talking about piezoelectric hysteresis model error, and I am Andrew Moss. Really quick for background, the phenomena that I will be discussing is called hysteresis. It is modeled in the left top figure, and it's defined by a nonlinearity between the input and the output. In our case, that's going to be voltage and displacement, or voltage and force, depending on which you care about. Piezoelectric actuators are a form of microactuator, and due to the presence of hysteresis, they've been largely overlooked in consideration for what microactuator is desired for a certain design, and that's in large part due to the hysteresis. The specific type of model that I'm going to be developing is for the cantilever beam setup in the bottom left figure, and the models that I will be using will be shown in the future slides. Really quick for previous research, there are two primary methods of analyzing hysteresis, it looks like, or at least piezoelectric actuator hysteresis models. And the first is just to assume that it's linear. And the equation of motion for that can be seen on the left with the mq double dot cr q dot kq equals f tilde 1 v1 plus f tilde 2 v2. Um, the assumption for linear limits the analysis to very low frequencies of input. And so it's not a great assumption. However, the alternative assumption that is currently in research is the hysteresis using only one mode. So on the left, we have multiple modes, and on the right, we have a single mode, but with hysteresis. And my thesis is trying to unify these two by using multiple modes with hysteresis. The issue with just using hysteresis in one mode is that you can only analyze around the natural frequency in which you have assumed the modes for. For the experimental data, I have collected the data on the test setup that I showed in slide 2. And these are the results plotted with voltage and displacement on the X and Y axis respectively. And then on the right is a superimposed linear model onto the data. As you can see, it doesn't fit great, but hopefully our hysteresis models will do a little better. So here are the four models that I have assumed. We have the linear model, the Bach-Wen hysteresis model, the Yang-Pankhurst model, and the Schmidt-Trigger model, all of which have varying degrees of success. It looks like the Bach-Wen and the Yang-Pankhurst models are the best, followed probably by the linear model or the Schmidt-Trigger model, although that's a little bit of a toss-up. But the primary component that we care to analyze in this is actually the error between the model and the experimental data. So the lower the error between the model and the experimental data, the better the model. And here we have a plot of the error between the model and the experimental data. As predicted, the Bach-Wen and the Yang-Pankhurst hysteresis models did phenomenally. The linear model, not great. And then finally, the Schmidt-Trigger did the worst. And truthfully, that's kind of to be expected of the Schmidt-Trigger hysteresis model because I kind of included it less as like a legitimate prediction and more just as a interesting note to see how a non-piezoelectric hysteresis model acts when it's in a hysteresis context. Finally, I conducted a T test, a single sample T test, I believe, in which the T scores for these were staggering, with the Bach-Wen producing a T score of negative 204.4. This is a p-value of essentially zero. Yang-Pankhurst also produced a p-value of zero, and the Schmidt-Trigger showed contrary to our beliefs. So at a confidence of alpha equals 0.01, we can conclude that the Bach-Wen and the Yang-Pankhurst models are better than the linear model. And the Schmidt trigger is, we can't conclude that it's better. We reject the null hypothesis that, or we fail to reject the null hypothesis that there's any difference between these. If the null hypothesis had been that the Schmidt trigger model was worse, then we would have some conclusive, some statistically significant evidence for that.